So when I hear performance portability, what I expect is I should be able to take a code and move it to another architecture than the one I was originally running, compile it, run it, and it gets, let's say, 80% of the peak. That architecture should be able to get. I'm willing to tolerate changing some parameters. Maybe there's some blocking parameters. Maybe vector lengths are different. I'm willing to change those, but I shouldn't have to make intrusive source code changes. So I talked here last year about how to achieve that with CPU code between different CPU architectures, and I'm using those techniques all the time now. One of the questions was, do those same techniques apply between CPUs and GPUs? And at the time, I didn't really know. I think we're kind of on a path towards the answer being yes. I have some good results here I'll show you. But before getting into how I achieved them, I think we have to understand the similarities between CPUs and GPUs in order to achieve that performance portability. And that's because we will need to use similar tuning techniques for it to be portable between the two. If you use different tuning techniques, then you'll have two different source codes, and that's not portable. So first couple of slides, I'm going to talk about the similarities between CPUs and GPUs. The results I show you later, I do on a Skylake and on a P100. For coarse-grained parallelism, the similarities between CPU and GPUs, on GPUs you have what are called SMs, and on a CPU, cores. So this is where our threads are going to target at kind of a higher level. On the P100, there's 56. Here I put 60. On this particular Skylake I was running on, there's 20 per socket. Now, on a CPU core, we have vector units. On Skylake, these are AVX 512, and there's 2 of them per core. They're making an effective vector length of 32 floating point numbers. The P100 doesn't have vector units. It has floating point cores. However, they are very similar to vector units because they get scheduled in what's called warps, and they have to execute in lockstep. So when you divide this up into warps, and you optimize your code to those warps, your code starts looking a lot like vector code. So that's a similarity I'm going to target when I'm trying to achieve this performance portability. Another similarity, on the CPU, we have a lot of cache, a lot more than the GPU has. But GPU also has cache. Actually, it has 3 things which kind of work as a cache. And what cache does is it optimizes code, the runtime of code, that reuses data a lot. And a lot of finite difference code reuses data. And so we want to make use of that cache. On CPUs, we all know it's L1 through L3 cache, and techniques for targeting that's fairly common. On the GPUs, it's a little more difficult because you have a software-managed cache called shared memory in terms of CUDA. But you also have L1 and L2 cache, which is hardware-managed, and you also have registers. So a lot of the techniques that you use on CPU to target cache can target those 3 things on GPU. And I'll just go ahead and jump straight into code. Oh, next one. Just a quick table. So for the coarse-grained parallelism, on CPUs we have cores, GPUs SMs. For arithmetic intensity, on CPUs we have vector units. On GPUs we have floating point cores, which are divided into warps. And for data reuse, on CPUs we have cache, and on GPUs, cache, shared, and registers. Unfortunately, it's kind of hard to translate these similarities into code because at the moment, there's not many programming languages out there that give unified support for CPU and GPU code generation. But that's starting to change a little bit. We just saw OpenACC is an option. Today I'm going to talk about how OpenNP can enable kind of a unified look at CPU and GPU coding. I just extracted a very simple kernel that typically consumes 90% of an acoustic wave propagation. It's just the stencil calculation. And I'm just going to show you some of the coding techniques. First, how I get close to peak performance on CPU. Then I'll show you how I do it on GPU. Then I'll show you how you do it all at once. For CPU coding, we first want to get all the cores. So first step with OpenNP, of course, parallelize the outer loop. You can play with the threading runtime, thread pinning, and all this stuff, but this is the first step, to use all the cores. Second step is vectorization. And there's actually 2 steps in one here. I used a new OpenMP pragma called OpenMP SIMD, which is becoming a lot more widespread use now, but it's still relatively new. But I've actually done 2 steps here. I had to interchange the inner 2 loops. If you notice, I had to move the fastest dimension to the innermost loop and then vectorize that. That's more efficient on CPUs. It turns out when you think about warps on the GPU, that's also more efficient on the GPU. So I'll get back to that when I show you how to achieve the same thing on GPUs. Finally, to target the cache, we need to promote the data reuse in this code. And the standard way to do this on CPUs is blocking with this kind of code. And blocking is where instead of you loop over every grid point individually, you loop over sub-blocks, and you try to get those sub-blocks to fit in the CPU's cache. The blocking parameters in this case are kind of a tunable parameter. From my point of view, if I switch this to another CPU, I might change those, but the overall code shouldn't change. OK, now how do I translate this to GPU? OpenMP offers offloading, which was mentioned in the previous talk. And the way it targets GPUs is a little different. I can't just use OpenMP SIMD and Parallel 4. I have to use something called teams. And teams are the way in OpenMP that I will target all the SMs of the GPU. So I haven't used all the floating point cores yet. This just hits all 56 SMs of a P100 in this case. OpenMP also gives you a way to manage data. Since there's now kind of a heterogeneous structure to the data, you need to know where the data lives. That's what the mapping directives are for. In this case, I just put the map directives right on the kernel. You wouldn't do this in practice. In practice, that would be lifted up on top, so you only do it once. But this is just for completeness, so you can see how it's done. Next step is, from the CPU case, was using those vector units. So by analogy, you might be tempted to do this. Every team gets a fixed number of threads that it can use those floating point cores. And the way you use those threads in OpenMP is OpenMP4. So it's actually like 2 levels of parallelism working here. This is tempting to do because the analogy is so strong to CPUs, but it doesn't work because for 2 reasons. OpenMP is fork join. So now for every single team, there's going to be a barrier inside that outer loop every single time. That's not efficient. Another problem is, I mentioned this thing about warps. Well, the schedule of that for loop is all wrong for warps. We want threads to be accessing data in kind of an interleaved fashion to get the most efficient, and this is called coalesced memory access. But this parallel for will, by default, usually is static, so it will divide up the iteration space into chunks, and each thread will get a chunk of data. That's not ideal. So there's 2 things I have to do to this code to get that nice interleave access. One, I did another loop reorder. Actually, I took the fastest dimension and moved it all the way to the top, unlike CPU, which went all the way to the bottom. And I put all of the directives on one line. So that removes the fork join problem. So now it's just one fast parallel loop. And I also added a static with chunk 1. That makes the threads of each team interleaved. So that gives us the nice coalesced memory access, and everything's nice and efficient. Next, shared memory cache registers. Well, it turns out the optimization for that is the same. So there's no way yet to use shared memory directly in OpenMP. I've seen some proposals for how that might be done in the future, but it's not there yet. But there's still cache, and there's still registers. And it still matters how you schedule this parallel loop, and blocking also changes the schedule. So that gives us some more tuning opportunities to make this run faster. And you might also notice I've collapsed here 3 levels. Again, that's so that all the threads are targeting the fastest dimension. The upper 2 dimensions are the upper 2 loop levels are looping over blocks. But we want those threads interleaving on the fastest dimension, so I had to collapse 3 here. Of course, you could only block on 1 if you want, and then collapse 2. There's some options there. OK, now how did I unify the 2? These are very different, but At the moment, preprocessor is the is the best alternative. It's a little bit messy, but what I like about this is that all the tuning parameters are the same. It really is just recompile and change some parameters between different architectures. It's the schedule. I put the schedule up there as a parameter. Collapse is a parameter. Blocking is a parameter. I let the compiler pick the vector lengths. They're probably not going to get any bigger than 512 on CPUs, and on GPUs, warp size is usually 32. So compiler is really good at picking that out these days, so that's not a big problem. But the inner loop stays the same, and I guess it's time to show you some results. OK. I did 2 test cases. First test case was a 512 cube. I ran it on a 2-socket Skylake 6148. That's 40 cores. Got about 6 billion grid points per second, so bigger is better here. That's about 70% of the peak on Skylake. I didn't aggressively pick the parameters, so you could probably do a little better. P100 on this same code, I just changed the parameters and recompiled. I didn't change the code at all. Got about 2x. Oh, by the way, the compiler I'm using here, Clang YKT. That's a special branch of Clang. I will talk a little bit more about that in the final slide. But the situation changes a little bit when I increase the problem size. When I doubled the problem size in every dimension, Skylake did great because I could just change the blocking parameters again, and cache picked up the losses. But on the P100, I lost some performance. I'm going to talk about why now. I profiled this, and I found that with Clang, every compiler kind of had its own issue. On Clang, it was synchronizing when it shouldn't be. In fact, it was spending half of its time in syncs. So there's a potential 2x there, meaning the original one could have been a 4x, and this one could have been a 2x. GCC results were not that great with GCC. At the moment, my best experience was with the IBM compiler, which I don't show the results here. I chose Clang here because it's much easier to get the access to that. You can go on GitHub, download it, build it. It was relatively smooth. Some other things that could possibly improve the situation. Preprocessor is kind of ugly. I would love to have language support for loop interchanging, doing fission and fusion of loops. I know it's been tried before, but I feel like we're kind of moving towards performance portability as like a realistic thing, and having to put in a preprocessor statement for that is a little bit of a pain. Another issue that was hurting portability here was with the Clang version of OpenMP, I couldn't adjust the schedule very much. In CUDA terminology, this is how many blocks you use and how many threads per block you have. With OpenMP, there is a way you can change the number of threads per team and the number of teams. It achieves the same thing, but Clang doesn't support that yet. It just picks the maximum number of threads, maximum number of blocks, which isn't ideal all the time. So I didn't investigate Cray, so there was a mention on Cray. I did look at GCC. I played a little bit with the IBM compiler and Clang. The results here are in Clang. I also know that coming up is AMD has a compiler called HCC for targeting their GPUs, and I know they have planned support for OpenMP 4.5 on that as well. So it seems like we're kind of moving in the direction of performance portability being a realistic thing to expect between CPUs and GPUs. I have some positive results here, some not so positive results, but I'm kind of hopeful. And there's lots of other options out there too. We saw some mentions yesterday, Akka, Raja, Kokos, OpenACC just a minute ago. From my perspective, I just hope the best wins. And that's it.
Questions?
So for the first issue, you mentioned synchronize between device and host. What solution you suggest that can minimize the...
For the synchronization, are you talking about for the performance issue I had? Yeah, so OpenMP has a way to solve that. You can actually manage the execution of code on devices through tasks, but Clang also doesn't support that yet. I can't remember which OpenMP version that came in with offloading. It may have even been in the first one, but that's how you would handle that. You would make it a task, and then you would only wait when you're actually done. At the moment, it's waiting every single iteration, which that's why it's costing so much.
You used GCC. Can you say what the problem was with that again compared to Clang?
Yeah, I profiled it, and for GCC, for some reason, every single time I executed the loop, it was copying the data, even when I told it not to with the map directive. I don't know why it was doing that. Maybe if I had investigated longer, there may have been a workaround, but that was the issue on this particular code. So, I mean, when I ran these timings, they're averages, actually. So let's say over 200 runs or something like that. So every one of those was a copy, and that's what was slowing it down.
Do you have any guess what the performance with like Raja or one of these portability layers would be?
I don't have a good guess, but I would definitely like to see how they are doing. I know a few folks who are working on it, and it seems like a really great idea and project, but I don't know personally.
Any more questions? Let's thank our speaker again.